Welcome everyone. Lecture 24, Introduction to Order Theory. Today it will be about nowhere dense classes of graphs. So a class is nowhere dense if of graphs, yes, if for every integer r greater or equal 1 there exists an integer t such that no graph in the class contains a subdivision of the complete graph of kt which is shallow. What it means is that each edge is subdivided at most r times. So you allow minors, arbitrarily minors, but you don't want to seed all of them at the bounded depth. So a usual toy example for nowhere dense graph class is a family of graphs that are, for each n you start with a clique kn and you subdivide each edge n times, and then you get a family, and this family is nowhere dense. Yeah. So that's just a toy example. The definition seems again perhaps weird, but this is actually the one of the least restrictive notion of sparsity for graphs that I know, and it covers classes of bounded expansion. Again, this seemed to be a weak requirement for a graph class to satisfy. Yet, this notion captures just enough structure to get meta-theorems. So, every first-order property can be decided in almost linear time for a fixed nowhere dense class of graphs. Nowhere denseness is also robust as bounded expansion. Actually, almost all the characterizations for bounded expansion have a counterpart for nowhere denseness. And this is what I wrote for you here as a theorem 1. Yeah, so a class of graphs is C. For a class of graphs, the following is equivalent. You have C is nowhere dense if and only if you have nablas bounded. Yeah, so these densities of the shallow minors that we discussed a lecture ago. So for any depth that you want to look d at, and any real number now, you should think of it close to 0, epsilon, n vertex graphs G in the class C have nablas, arf nablas, bounded in order big O of n to the eps. Yeah, if this is satisfied, this is equivalent with nowhere denseness, and you might remember that bounded expansion, the D definition we had for bounded expansion was that for every if this is D, then this perhaps should be D as well. Sorry for that. For bounded expansion, for every D, we had a fixed bound for nabla D. Now we allow nablas to grow with the size of the graph we look at, but this growth is limited to this function. So it's slower than any polynomial. Yeah, you could say. Okay, so this is one thing. Now it will be useful for us again to work with weak coloring numbers today. So there is a characterization in terms of weak coloring numbers. So now for every r that we want to look at, and every epsilon again, and vertex graphs in our class C have weak coloring numbers again of this order, big O of n to the epsilon. This again captures the same notion of sparsity, which is called nowhere denseness. Okay, and I want to show you yet another characterization of nowhere denseness. This one brings together, we could say, brings together structural graph theory and combinatorics of pole sets. Yeah, so far we were bounding poset dimension in terms of its height. Now we will get the bound again, actually, and this is the essence of this statement here on this board. But actually, the converse implication is pretty straightforward, and we have a characterization. So let's have a look. Now we want to look at the monotone class of graphs. So monotone simply means that it's closed undertaking subgraphs. And then the following is equivalent. This our class C is nowhere dense if and only if for every h we want to look at integer height, any epsilon, n element posets of height at most h. But what is the relation of a poset with respect to our graph class? Well, now those are the posets whose cover graphs are in our class. So whenever you find whenever you have a poset which cover graph belongs to the class and this poset has bounded height, then it must have bounded dimension. Now you could recall that the dimension for a fixed height, the dimension was actually constant when we had a planar class of planar graphs here for C, or a fixed class of bounded expansion. Now we allow it to grow. Again, the same rate of growth as you've seen in the other characterizations. Okay, so that's the statement, and this lecture will be about to deliver the proof of it. We will start from the easy direction. Maybe helpful to actually build basic intuitions. What are we talking about? So we are about to prove now that we double check is that 2 implies 1, and we will take a contraposition. So we will take a class of graph C which is somewhere dense. Yes, well, what does it mean? We have to negate the definition. So there exists R, did we call it R? Yes. Let's say greater or equal 1, such that for any target size of the click we think of, there exists a graph in our class such that this graph G contains at most R subdivision of KT as a subgraph. So here I introduce on the fly handy notation that at most R subdivision of a graph is a graph that you obtain from the original graph by substituting perhaps some edges by paths on at most R vertices, R internal vertices, yeah? So one subdivision would be that you replace each edge by a path of length 2, where 2 is now the number of edges, yes? So by at most R, we have here. So some edges could maybe are not subdivided. Anyway, this defines a class to be somewhere dense. And then given any class like that, we claim that the second item doesn't hold. So the proof is really brutal and straightforward. So what do we want to find? There are basically standard examples in some sense. So what are we doing is here we use actually the fact that C is monotone. That's the only place that is required, and without that it would be simply wouldn't be true. And there are characterizations of nowhere dense classes where this monotonicity is put there into the description. So this is not so unusual. Anyway. when C is monotone, and we didn't need the monotonicity here, by the way, that's just because these operators are monotone undertaking subgraphs. So C is monotone, and this implies that we can find for every target M, let me change the letter, there exists Gm in C, and Gm is an at most R subdivision of the cover graph of a standard example of order n, of Sn. Yes, so how do we get that? Well, if we are heading for a standard example of size n, the number of elements there is 2m. So what we could start with is to find a clique on 2m vertices. We can find it in our class, and it's subdivided. It's subdivided at most r times, where this r is fixed here for the class. Yes, and now since it's closed undertaking subgraphs, we just get rid of these paths that we don't need in the cover graph of a standard example. Yes, so this is Gm. It lives in C for each m, and what do we need to know? Well, Gm simply has not too many vertices, has at most r times m squared plus 2m, something like this. So for each comparability, and there are roughly m squared, well, at most m squared of them, we can have r intermediate vertices, yes, and then we have 2m original vertices, yes. So we have in mind that we have this picture here, and on each edge we could have r extra vertices. And obviously this thing is a cover graph, yeah, of a poset. Gm is the cover graph of a poset Pm, where this poset is obvious from the picture, yeah. How does it look like? And dimension of Pm, since it contains a standard example of size n, is at least m, yeah. And now that's it, because if we put that n is the size of Pm, then dimension of Pm, which is at least n, is omega of n to the 1/2, yes, because of this, yeah. Since n is at most r m squared plus 2m, yes. Okay, so we get the negation of the second item for h equal r plus 2, because that's the height of Pm at most, and then epsilon that we need to get is anything below 1/2. So we could take a quarter, for example, and then the second item is simply not true, which proves the implication. Okay, so the non-trivial part is to get from item 1 to item 2, and perhaps it is tempting to think that our bound for dimension using wcols numbers is helpful here. So let me recall you that we know that the dimension of P is at most 4 to the appropriate wcols number, which is I think it was 3h minus 3, and of the cover graph of P, yes. And now, given that P is in a lower given that the cover graph of P is in a lower dense class of graphs, we do have a bound on the wcols numbers, right? But But this bound, in this case, is not satisfactory. Yeah, because we result in something like this, where I remind you, we would like to get something like this. So, and this is actually pretty much vacuous because dimension is always less or equal than the number of elements of the poset, yes? So yeah, this is too weak. This is too weak. And in order to get this non-trivial part done, we are going to develop a second bound for dimension in terms of the weak coloring numbers of its cover graph. But we need to involve yet another thing from the lower denseness to make it work. And here is the actual theorem which will support the implication here. So the theorem is that there exists a function f such that for every target height that we think h is, and for every t, when we look at the poset p of height h, whose cover graph now comes this specialty about p. It's bounded height, but its cover graph contains no shallow subdivision of kt as a subgraph. Yeah. Now this shallow is some function of h. Yes. So maybe let me write here s of h is 2h minus 3. So okay, we have a poset, bounded height and cover graph with no 2h minus 3 subdivision of kt. Then what? Then dimension is bounded by this, where c again is a certain recurring number. Now this time is for h minus 4 of the cover graph. So this 4h minus 4 is actually another function of height. And now please note that the actual functions sh and wh are irrelevant here. Any functions, whenever we have some functions of h here in this place, this will work for us to support the implication we need there. It happens that for these numbers the proof works, and in some sense they come naturally in the argument. So yeah, with this in hand, we will be able to deliver, because in the lower dense setting, yeah, we will have so this t will be again a function of h. Yes. So this is written here as a corollary. Look, that for a lower dense class of graphs C, yeah, we will get eventually a function g. Yeah, and this function will work that whenever we get a poset of height at most h, whose cover graph is in our class, then the dimension will be bounded by 3c to the gh. C is the same c, and now gh replaced fht. Again, because as soon as we fix our lower dense class of graphs, then we know that if we want to avoid shallow subdivisions, then there is a t that we don't have in the class of graphs, yeah, and this t will be the function of this number that we are avoiding. So this is again a function of h, and that's why g itself is a function of h. And this type of bound delivers implication from 1 to 2, because now we have polynomial dependence on the weak coloring numbers, and weak coloring numbers is the only thing that grow here with the size of the graph, yeah. And now it's here, so it's n to the epsilon to the power of something we take as a constant, yeah. So yes, so this will deliver, this will close the proof of the main theorem here, and we shift our attention to actually prove theorem 3. Okay, so the proof of theorem 3 is fun, and as you expect, we have to get deep again into recurring numbers, which is fun. There are at least 2 blocks of the proof that we can distinguish, and the first one will actually operate on the recurring numbers, and I put it here as a lemma. So let's read out the lemma. So we look at a poset P. It has height h, and now the cover graph is G. Now we look at some set of incomparable pairs, yes, I, and we have the same C that is fixed in our statements today, which is the 4h minus 4 recurring number of G. Then what does it say? Yeah, let's actually try to draw something here. So how about we make space here? So we have a poset P, and in this poset we have some distinguished incomparable pairs, yes? So perhaps we have a pair xy. Here y's will be kind of distinguished in the moment you will see. So let me put y, but it's a pair, there is some x hanging for it. And now we have a bunch of these pairs here. Yeah, some y's could be the same, different rows of elements in different pairs, whatever. But the statement is that given this set I, we will be able to find a subset I prime. And this subset is special. What is special about it? Well, there exists an element Q, first of all. So let it be blue. There is a Q in the poset, yes? And then Q, we will look at the upset of Q here. And then our pairs, some of the y's are hit by the upset, and some of the y's are not. And so what we want to take here are those that are hit, that are in the upset. Those y's, those second elements of the pairs that are in the upset. And we claim that if we just, our set of incomparable pairs was just wild. And you should think that it actually has a large dimension. Okay, now what does it mean that a dimension of a set of incomparable pairs? Well, dimension of I is the least integer d, such that I can be partitioned into d reversible sets. Yeah, we take if we agree that for I empty, for the empty set, yeah, dimension of I is equal 1, then we will get that dimension of the poset we look at is just the dimension of its set of incomparable pairs. Yeah. Okay, so back to the statement. We have a wild set of incomparable pairs, and we know that it's complex. There's large dimension. And now what I want to sell here in this statement is that there is a local witness for that. So there is an element in the poset Q that when you just look at its upset, yeah, then you will have hit some complex witness. Yeah. So here it's stated. So the dimension of the subset is still large. We give up just a fraction, C fraction of the original dimension. Yes, and then this type of statement that when we have something wild, something complex, like some chromatic number of a graph with large chromatic number, and then there is a local witness. If something like that works, then usually we are able to get some nice, efficient ways of bounding our stuff, and this is what we are going to do here. Okay. So let's prove the lemma. We start with our poset P, and as it's very usual, we fix a linear order that witnesses the weak coloring number that we want to look at. Yeah. So pi is a linear order on the elements of P. And that witnesses witnessing that wcol R 4h minus 4 of G is C, is at most C. So in particular we have that W reach of 4h minus 4. When you look at the graph G, linear order pi, and any element x, that the size of it is at most C. Yeah, and this works for any x in P. Again, let me recall you that we have poset and a graph G, and both on the same set of elements, so we can interchange it smoothly here. So this is pi, and as in the proof in the last lecture, we're going to greedily color elements of P going along pi. So we set up a coloring, and it's a greedy coloring. Of elements of P. This goes along pi, and now let me just depict you what I'm doing. So when we are about to color x, we just look at the W reach of 4h minus 4 G pi x. Yeah, we look at this set, which is all of it is to the left except x itself. So if you subtract x from it, the size of it is strictly less than C. And here you want to avoid the colors that are used here. And we have C colors, so we will always be able to complete it. So phi uses at most uses colors from 1 to C. Yes. Okay. Avoid colors used here. Okay. So that's our setup. We have pi. We have phi. Now we build on it, so we have a useful observation, very easy, that when we have an element in the poset, and we have the two elements in things that we can reach from Z, so G pi Z, and now the distance is not complete, it's 2h minus 2 that we want to look at here. Yeah? So in terms of, okay, let me complete the statement because it's easy. I want them to be distinct. And then what we will get is that actually their colors are distinct. Yeah? And this is a very quick consequence of the greedy style that we took when we did the coloring, because when you look at the pi itself and you look at this vertex set, then you can reach x x can be reached from z, so perhaps it looks like this. And then also well, y could be reached. And well, y, where's y? I don't know, say y is here, yeah, and then you do some stuff like this, yeah. So can it be that both of them have the same color? Well, not really, because we can combine these paths. In the union of these two paths, we can find a path that connects x to y, and the length of it is at most h minus 1. Not h minus 1, what am I saying? 2h minus 2 and 2h minus 2, yes? So, so the length is at most 4h minus 4. And this, since these were witnessing reaching y and x, then in the union, one of these two elements is the leftmost of the whole picture. And this will witness that one of the elements is reachable from the other in this number of steps. So when we were coloring y, we couldn't use the color of x. Yeah. Yes. So this observation works. And now, now what we're going to do is to try to define things that will help us to build a signature, which is the way we're going to kind of partition our initial set I into some subsets, but we'll get into it. So so what we are doing here is we take an element z, and then now we are defining a color associated with this element, tau of z. But it's not necessarily, it's not really necessarily the color under phi. It is different. So this thing denotes the color of element which is minimal under pi in the closed down set of z. Okay, so what do we have here now? Now we have to look at the posed picture for a moment. So this is our posed P, and we have an element z. We're talking about the down set. So so that's the closed down set of z, yes. And then when you look, so these are, let's imagine that these elements are somehow all blue. And now when we look at the pi, you know, then there is z somewhere here, and the blue elements can be everywhere, yeah? They could be to the right, they could be to the left, yes? And now the guy which is most to the left is the guy that we are interested in, and the color of this guy is tau of z. Okay, so maybe this is red, and red sits somewhere here, and this is tau of z. Yes. Okay. So so now I want to put a definition for a color. So when we have a color I, we can look at the kind of ith thing we can reach from Z. So well, not ith, but of color I. So what is how do we read it? So this will be the unique element of W reach 2h minus 2 g pi, what is the element z? Colored with I under phi. And now if it exists, and this is going to be undefined otherwise. Okay, so what are we looking at here? For a moment we don't look at the poset at all, it's just a weak reachability. So we already seen, yes, that given an element z, when we look at the W reach, when we look at this set here, then the elements over there are of distinct color under phi. Yeah, this is the first observation. Yeah. So now if we look at the yellow color I, there are only two options. Either there is a unique element there of the color yellow, or there is nothing of color yellow. And this is where the cases come here, okay? Okay, so now to combine it, let's try to imagine what is W tau Z of Z. Okay, so now what do we have here? Well, tau was looking at the poset, yeah? We are looking at the downset. Yeah, this thing here is the downset of Z. And we were looking at the color of the leftmost element under pi in the downset. So that could be this element colored with tau Z. This is minimum under pi. Yeah, that's a minimum under pi of dz. Okay, so now I'm asking, what is the unique element of color tau z in this set with respect to z? And I claim that this is the element. Well, what we need to show here is actually, so I claim that this is simply minimum over pi of the downset of z, yes? This is what I claim. Well, so we should show that this can be reached from z, and that's pretty much obvious. You just take a chain down here, and since this guy was the leftmost over all downset is the leftmost over this chain, so this can be reached from here. Yes. So this is why it's so easy, and in particular we have the property that W tau z of z is less or equal z in the poset. Yeah. Okay. So so in particular it also exists. Yeah. Maybe I should write it here that it also exists, and it's equal this one. Now we come up with a new observation. So it states as follows. So let x and y be two elements in our poset, and we have that x is less or equal y in P. Then W tau y of x exists, and W tau y of x is equal W tau y of y. Okay. This is a little lemma we need to, well, not lemma, but observation we need to have. Okay, so where do we go? Let's leave the statement for a moment, because so far we are just building something yet unrelated with the statement itself. So I want to argue about this one here. So maybe this was observation star. So this observation will be double star, okay? And we want to prove observation double star. Well, proof of observation should be very easy. So let's try to draw a picture. So from the perspective of a pole set, what do we have? We have element x, and we have element y, and then we have the downset of y, yes? And x sits somewhere here, right? This is the downset of y. Now, we have this guy w tau y involved, which is fairly easy. We know that this guy is simply the leftmost guy in the dy, yeah, under pi. Yeah, so this is it. That's the, say, w tau y of y. Yeah, and then it's in the downset, so perhaps it looks like this. Okay, and now we want to argue about the element w tau y x. So first of all, it exists, yeah, and we're going to prove that it exists because we're going to show that we can reach this guy from x. And you can see it already, yes? Because what I want to do is I want to walk up this chain until I hit the red chain and then go down on the red chain. And I claim that this guy is the leftmost because this guy is the leftmost in the whole downset. Okay, so that this is the, and then the length of our excursion is at most h minus 1 plus h minus 1, yes, which is 2h minus 2. And the wi was defined for 2h minus 2, so it is exactly the distance we can afford. Okay, but now we are. Well, that actually completes the proof also, right? Because we show that we can reach it. We show that we can reach it, and we know that in the W reach of G pi x, there is at most one guy of this color, and this guy is there. So it must be like that. Actually, I had another 2 lines of notes for this, but if I didn't go crazy now, I think it completes the proof here. Okay, so that's good. That's good. So now we are ready to actually relate to the statement a bit. We have the 2 observations here. Let me erase the proof of this observation. And here's what we are going to do. We're going to partition the set I, yeah? And in this partitioning, we'll use like a signature. We'll color the incomparable pairs, but since we have our coloring already, we use the notion of signature. So, so here is the signature, sigma xy, and this will be of a pair that sits in I, xy. So incomparable pair of the pole set that sits in our set, and this will be a pair where we take tau of y and we take yet an extra bit alpha xy, which I'm about to define. So, well, okay, so, but looking at the poset P, yeah, you have an element X, you have an element Y, they are incomparable. And now we want to put into the signature the color of tau Y, so you remember there is downset and there is this color of the leftmost element of the downset. That's the tau Y. Yeah? And now I want to put yet another thing, which relates a bit X to the signature. So alpha X Y is defined to be 1 if W tau Y of X is actually equal to the W tau Y of Y. Yeah, so now we are W tau Y of X. We're asking for a red element, so if tau Y is red, yes? If tau Y is red here, like if it's a red color, so we're asking if we can reach red color from in the 2h minus 2 weak neighborhood of X. And one possibility is that we can, and this is the exactly same element. That's a possibility, yes? So that would be, that would give alpha xy 1. Now 2 is when they are distinct and 1 is less than the other. And 3 is they are distinct and 1 is greater than the other. T, Y, Y, Y. Okay. So that's a way to, so that's obviously in pi, yeah? In this linear order that we look at, yes? So now we have a linear order. There's somewhere X and Y. We have no idea what is the ordering there, but let me envision it as this. And then there is this element, yeah, which is somewhere here, right? And then the question is, okay, there is yet another case here, right? Because maybe the red element of X doesn't exist. And that we incorporated to the 3. So, or W tau Y X undefined. Okay, so if they are not equal, the red elements, then perhaps the red element of X is to the left of the red element of Y, and then that would be case 2. And the opposite would be case 3, and also when we have no red thing around X. Okay, so that's the signature, and now here is the idea, finally, some idea how do we prove the lemma. So we split I with respect to the value of the signature, yes? So immediately let me write it. So whenever we have tau, some color, yes, and we have alpha, which is a value 1, 2, or 3, yeah, then we define j tau alpha to be, we define j tau alpha to be the set of incomparable pairs, subset of incomparable pairs of Y, such that the signature is equal tau alpha. Yeah? So that's the pairs of the fixed signature. And then obviously we have that I is partitioned into j tau alphas, yeah? Where tau runs over this and alpha runs over this, yes? Okay, so we have a partitioning of some incomparable pairs. Now, maybe it's handy to think that the dimension of I is large, yeah, as I was trying to pitch you the statement. And then, if it's large, and we partitioned I into some blocks, then some block has to carry large dimension. And what is the block? And we will quickly see now that the block has to have 1 at the coordinate. That all the other stuff is easily reversible. So let's go for this observation now. So claim is that for every tau in C, J tau 2 and J tau 3 are reversible. Okay, so let's prove it. So yeah, let's have a look. Yeah. So let's, whatever is the alpha, if it's 2 or 3, we don't care. Let's fix it. And we fix also tau. Now, well, suppose that J tau alpha is not reversible. No? Then, as we know well, there must be an alternating cycle, right? Alternating cycle in P with all pairs with xi, yi in J tau alpha, yes? All pairs there. We close an alternating cycle. Now, what can go wrong? Well, let's have a look. So we have it, for example, that x1 is less or equal than y2 in the poset, yes, because it's an alternating cycle. Now, from the observation that I just have erased, we know that w tau y2 of x1 exists and is actually equal to w tau y2 of y2. Yeah? This is because x1 is less or equal than y2. Now, this value, since x2, y2 is in J tau alpha, this value is actually equal to tau, yes? So, so now, and now this works if I would put here any number like I and I plus 1, right? There is no, well, I didn't have to distinguish the number 1. And then we simply get that if well, first of all, did I say that it exists, yeah? And is equal to this. And now second is that if alpha is equal to now, then what we get is that w tau w tau I plus 1 is equal w tau xi, which is now in the case 2, which is less than w tau yi. And this holds cyclically for each I. Yeah? W tau yi plus 1 is strictly less than w tau yi. So that's a contradiction. That's a contradiction with an existence of an alternating cycle. And now if alpha is equal 3, then we have the same story, yes? W tau yi plus 1 is equal w tau xi, but now this time it is greater than w tau yi plus yi, yeah? And this holds cyclically, so again it's a contradiction, and this closes the proof of the claim. So, so good. So let's now build on this. So the dimension of our set I, let me recall you. It's the minimum number of linear extensions that we need to reverse all the incomparable pairs in I. So this is, so we can simply bound it by taking j tau 1. This tau goes over C, yes? Plus dimension j tau 2 plus dimension j tau 3. So we have a partition of I. Yeah? So in order to reverse everything in I can take each block from the partition and reverse. Spend private linear extensions to reverse stuff in the block. And obviously this will kill I, and most likely it's not the most efficient way to kill I, but we don't care. And now from what we have seen here, we don't need much to do this nor this, yes? Because this is reversible, so one linear extension will do. So this proves that this is bounded by the sum over tau dimension of j tau 1 plus now C here and C here, that's 2C. Okay, so now we're good. Dimension I is bounded by this, so there exists a color tau such that it is large, it contributes at least, well, a C factor, yes? So what do we have is that the dimension of j tau 1 is at least the dimension of I and plus but minus 2C over C minus 2. Okay? Okay. So this is starting to look nice. Let's try to recall our statement now again. In our statement, we want to get a subset of incomparable pairs that are local to some element, yeah? That we have all the second elements, all the y's in some upset. We are not yet there. We are not yet there. So we fix this tau, and let's denote by I tau the j tau 1 for convenience. Okay, so now let's take another step, and let's split now this set I tau. Okay, so consider an element P in our poset, and now take I tau P to be a set of incomparable pairs in our I tau, such that what? Okay, we have to recall what are we talking about. This is j tau 1. 1 means that the w tau y of the first element is the same as the w tau y of the second element. Yes? So I want to split our pairs with respect to what is this element. Yeah? So for every element P, I take out a subset of I tau such that my pairs have their special elements on P. Okay? So again, trivially, I tau is just the union, disjoint union actually, of I tau P. Now P runs over the elements of the poset. And that's a partition. And now we need the last combinatorial observation to close the proof. We will state it as another claim.
So the claim is that dimension of I tau is actually witnessed by the maximum dimension of P dimension I tau P.
Okay, maybe it's a bit abstract statement, but I hope it will clarify over the proof, as we're going to do a simple step first, which is the one of these inequalities is trivial. So for convenience again, let D be equal to this maximum, okay? It's maximum over P dimension of I tau P. Now, please observe, but okay, let's discourage you a bit and let's write obviously. Obviously, dimension of I tau is lower bounded by the dimension of I tau P for any P in P. Okay? Well, simply because I tau P is a subset of I tau. Yes? That's nice. So this actually means that since it's for every P, then we immediately get that dimension of I tau is at least D. So all our efforts should go to prove the opposite, which is non-trivial, because, well, we split our incomparables pairs again, and we claim that one of the block witnesses the whole complexity. So it must be because of the structure there, right? So let's take a proper look. So wanted is that dimension of I tau is upper bounded by D. And now this will be very brutal. So for each element P in P, what do we know? When we look at I tau P, we know that it can be partitioned into D reversible sets. By definition, D is the maximum. So this can be partitioned into D reversible sets. Let's call these sets I tau P1 up to I tau P D. Some of them possibly empty. Okay, so now what is going to happen? We will take a brutal union. So now we are looking at a J which goes from 1 to D. And we are going to sum. So for each element P, we will take I tau Pj and we will collect them together into one huge Ij. so consider the union of all I, tau, p, j, and now the sum goes over p. And we claim that, or we subclaim actually, yeah, that the set is reversible. This will complete the proof of the claim, because this way we'll partition all pairs in I tau into D sets. Yeah. Now we have a partition for each block I tau p, but we're merging together like vertically. Yeah, the partition blocks. So we merge them and we say that it's still reversible. Well, let's have a look. If it's true, it must be very simple. So so suppose it's not. And this way we get a standard example. Not standard example. Alternate cycle, right? Alternate cycle with xi, yi in what is this business? In the sum. Yes. Okay. So let's look at our alternating cycle. So we have xi less than or equal yi plus 1 in p, right? This means that what do we have? We have that w tau xi is equal to w tau yi plus 1. How do I know that? Well, this comes from the early observation that we were building in the proof of the lemma. Yes? So because x is below y, so the w tau of x exists. Yeah, because tau, recall that tau is the tau yi plus 1 actually. Yeah, that's how the signature was defined here. So it exists and it's equal to this one. Yeah, so this comes from observation. Was it observation star? Perhaps. Or maybe it was double star actually. Now, but from the signature itself of the, because we are living in the j tau 1. So we are living with these pairs xy that their special element coincide. So we know that this is equal to w tau yi. Yeah, because this comes from the fact that xi yi simply lives in j tau 1. Yeah? Okay, so this way we have that w tau yi is equal to w tau yi plus 1, and it holds cyclically for all i's. This means that actually, so let's call this element p. Yeah? Let's call this element p. So we have this element p, yeah, and we know that every pair xi, yi actually belongs to what? Where are we sitting? It was here, but among all the, or maybe it was, let's call it p prime for convenience, yeah? So among all the stuff, it always hits the p prime. So it's always I tau p prime j. J was fixed. Okay, but this is a contradiction because this set is reversible. So we cannot have an alternating cycle here. Yeah? So that's a contradiction with the fact that subclaim that well with the opposite of this. So we prove that that when we merge the J sets together across OP, we get a partition of our whole business, of I tau into d-reversible sets. So this proves the claim. And with the statement of the claim, we are on the finishing line with the lemma, because we have to just collect what was already on the board. So to complete the proof of lemma, which is still there, we take element Q in P that witnesses this equation, this equality here. So we take Q such that dimension of I tau is actually equal to dimension of I tau Q. And now I tau Q is our thing. So what do I want? First observation is that I tau Q is actually a subset of the I prime, which is defined in the statement. I primals were those incomparable pairs from I such that the Y is above Q. And I tau Q consists only of such pairs. Because Q is the special. Let me one last time recall you the setup. This is X, Y, and the tau. The tau is from the signature, so it's tau Y, and tau Y was the color of the leftmost element in the downset of Y. And Q here means that this element is Q. So this is Q, and Q is below Y. So we have this thing, and then we also have the dimension, because dimension of I tau Q, or if you prefer dimension of I prime, which is greater or equal than dimension of I tau Q, is equal to the dimension of I tau. This is by the claim. And now the dimension of I tau was large, because tau was chosen to witness it disappeared already, the C fraction. So this is at least dimension of I over C minus 2. This was before the board. So this completes the proof of the lemma. Let's recall where we are. So we want to prove theorem 3. This theorem: there exists a function f such that for every h and every t integer is positive, every positive p of height h whose cover graph G contains no shallow subdivision of kt. Shallow in terms of as a function of t. Then for every such poset, dimension of this poset is bounded. It's bounded in terms of its weak coloring number of a cover graph, and in terms of h and t. Now, we're going to prove this theorem. We already prepared a tool, which is a lemma. That's the statement of the lemma. We know that when P is a poset of height h, and whose cover graph is G, and when we have a subset of incomparable pairs I, and this C is the same C as there, then we know that there is an element Q that that makes such that when we project somewhat the set of incomparable pairs I into Q, so we just take those pairs with the second element greater than Q, then this new set, this subset of I, still certifies the complexity of I. So we go down in dimension only by a factor of C. Okay, so we're ready to start the proof. So within this proof, we want to prove the existence of a function f. So this is going to be our function, a function of h and t. It will be equal m plus h choose h, where h is an argument and m is defined in terms of h and t. So it's pretty large function, but it is in terms of h and t. And now to prove that it all works, we are fixing height h, we are fixing the value of t, and then we consider a poset p such that its height is at most h, and its cover graph has this coloring number, we fix it to be c, and we're going with a contraposition. So we're going to show that, well, this is the statement, we're going to show that if dimension in this setup is large, then we will force a shallow subdivision of kt. So we prove the contraposition here, we assume that dimension of our poset is large, and what we want to show, we will explicitly find this shallow clique minor. Yeah? And we want to show that G contains at most 2h minus 3 subdivision of kt. So this is our project now. And one more comment. It is somewhat handy to assume that C, which is the wcols number, is greater than T. It makes sense for at least two reasons. First of all, actually it's only those C that we need to somehow study in terms of our goal, which is to support the characterization of lower dense classes. So we could put it into even into the statement, and that would be enough to prove what we want to prove. But actually the statement is also true for small c's. So I didn't put it there. And for some small c's, we can use the previous bound that we have, this bound 4 to the wcols number that we have. So given this, so in that previous bound, the wcols number was 3h minus 3. It is bounded by the 4h minus 4 wcols number, and in this case, it's at most t. So then we know that the dimension of P simply is bounded by 4 to the t. So without any contraposition, we are finishing the job here, with even with no assumption on that there is no subdivision. Yeah, just like that. So yes, so that's why we are given this, and it will be useful in one of the steps. Yes, so we kick off here with a claim. So again, we want to find a model of KT, and we'll make it in basically 3 steps. The first step will be easy. This claim is the first step in order to find the model, find the branch vertices, find the paths connecting them. So yes, so the statement of the claim. We are going to show that there is an antichain S in the poset P. This antichain is huge. It's of size m. M is given over there. And it will be special, this antichain. When we look at here we define a set I of incomparable pairs. Yeah, let's start with a small drawing here, just depicting the statement of S. So this antichain, yeah, let's envision it as these elements. Yeah, it's huge. The size is m. And now when we look at all incomparable pairs of P, such that the second element is above all elements in S. Yeah, so somewhat I didn't make it readable, I wouldn't make it readable this way. If we look at the upsets, yeah, and so on, then we should imagine that these y's are somewhat sitting here, yeah, these elements y's, the y's that are contributing to the pairs in I are above every one and each element in S, yes? So, okay, so so from S we get I, and we want to say that we can find this huge antichain S such that looking at the corresponding set I, this I is non-trivial, so dimension at least 2, which basically will mean for us that it's non-empty actually, because the convention is that the dimension of the empty set is 1. So this will basically works for us that there is something, but this is kind of a border condition. The interesting one is here, which says that whenever you will try to restrict I, so whenever you will try to pick an element Q, which is above at least one of the elements of S, yeah? So let's try to envision Q as a red element here. So let's say that Q is, I don't know, somewhere here, say, yeah? So indeed it's above some element in S. And then we will just look at those elements, yeah? At those elements of our I that are, they were above all the blues, but now I want to look at those that are above Q. So maybe I missed something. And indeed I will miss something, because here it says that the dimension goes down faster than this, faster than the free C factor down, yes? The dimension of the new thing, smaller thing, is bounded from above by the dimension of the old thing divided by free C. So it's less than 1/3 C factor of the original dimension. Okay, so this looks like a quite technical statement. It is. It is a starting point to find the branch vertices. So we're going to prove it now. So, the proof of the claim is quite neat. And we start our consideration, so for any antichain S, that is of size at most m, we're going to set up some quality measure of this antichain. And it is going to be, we will call it a height vector. So height vector of S will be just a vector of heights of elements in S. But we will sort those heights in a non-increasing fashion, yeah? So sort it in non-increasing order, and I remind you that S is of size at most n, S could be small, so I want to pad the vector at the end with 0 entries, so the height vector will be always of size n. Yes? So, and pad it with 0 entries at the end, So the size of the vector is m. Okay, so that's the height vector. And now, well, first please note with me that the number of possible height vectors is a nice combinatorial. There's a nice combinatorial interpretation. Yeah, we have vectors of length m. They are sorted with entries from set from 0 to so the height of the element height is bounded by h. Yeah, from 0 to h. So the number of height vectors is m plus h choose h, right? And then so what we want to do, we're going to enumerate these vectors in a lexicographic order. In lex order, with numbers from 0 to m plus h choose h minus 1. So m plus h choose h should be exactly the, yeah, this is just has been erased. So please recall that the f of ht was defined as m plus h choose h, right? So, so this is exactly f of ht minus 1. And so we enumerate those vectors, and now given antichain S, yeah, the value of this antichain, yeah, will be just the index of the height vector of S in this order, in this enumeration. Yeah, so please note, for example, that the value of the empty set is 0. Yeah, because the height vector of the empty set is just a sequence of zeros. This will become first in this lex order. Yeah. Okay. So so we have some quality measure for our antichains. So now we will choose an antichain which will witness the claim, and it will be chosen as somewhat extremal one, also under this quality measure. So so choose S, choose an antichain S, with so the size is, we insist that it's at most m, such that first of all the dimension of the corresponding incongruous set I will define it here again, will be greater than 3c to the power of fht minus value of s. So let's call this value for a moment d. And the set I is just all the incomparable pairs, such that the second element is above everything in S. Okay, so we want to choose such an antichain with value of S maximum possible. Yeah, so we want to pick an object which fulfills this and is optimal under this criterion. So first of all, we need to argue that there is an object at all like that, and there is. So S is well defined as S equals empty set is a good candidate. Yeah, for S being an empty set, what do we have here is this corresponding set I is just a set of all incomparable pairs. So dim of I becomes the dimension of the poset. And now at the input, yeah, for our contraposition, we are assuming that we are working with a poset with a large dimension. Yeah, S large, exactly 3c to this power, and value of an empty set is 0. So S is a good, empty set is a good candidate. And now we want to choose S, but the value of empty set is 0, and perhaps there are better choices, and we fix S to be the best choice. Okay, so now. What are we going to do here is we're going to show that this choice of S witnesses the statement of the claim. And so first of all, we check easy stuff. So in particular, the dimension of I is, well, by definition is greater than this V, which is at least 3C. So this comes from the fact that we are subtracting here value of S, and the maximum possible value is this, yes, FHT minus 1. So we have still 1 power of 3C. So D is at least 3C. And then for something obvious like I don't know, like say C greater than T greater or equal 1. Yeah, we have that this is at least 3 or even larger than 3, but in the statement we need that this dimension is at least 2, so we have it. So this is one thing. But now we are going to check this more interesting stuff, that whenever we choose an element Q that is above one of our elements in S, then the dimension of the corresponding set of incomparable pairs goes down. So assume to contrary that there is Q in P such that there is also S in S with S strictly less than Q, yes, in P, and dimension of I prime is larger or equal than dimension of I over 3C, where I prime is the set as in the statement. So I prime is the set of xy in I such that Q is below y in P. So we just assume to the contrary that we don't have the thing we want in the statement of the claim. I'm just about to use this lemma, but I need to erase it. So what are we going to do with this? So yeah, maybe a picture, right? So this is our set S, yeah, and so we have some offsets, right? And then we take some element Q, right? And we look at its offset, yeah. And the I prime stuff is yet above Q. All the incomparable pairs with the second element yet above Q. Above all the S and yet above Q. What are we going to do? We're going to take S prime. We're going to claim that if we take S prime, which is S, where we subtract the downset of Q, yeah, and we add a singleton of Q, right? Then this S prime is better. Yes?
Why Q can be below someone in S?
That's easy, because S is an antichain, and Q must be above something from the antichain, so it can't be below anything else. It could be equal. No, it can't be equal. It can't be equal because this inequality insists to be strict. So yeah. So we say that we kill those blue elements that are under Q, and we put Q instead. And we claim that this set is better, this antichain is better. So, so first of all, please note that the value, indeed the quality, the value is better. And this is a simple observation, because what you need to see is, first of all, we removed a non-empty set. Yeah. Secondly, we introduced an element which height is strictly larger than all the things that we removed. And then by the lexicographic order, this new set must have a higher value, must be later in the lex order. Second thing is just to observe that the size of S prime is not too large, yes? And this simply is because we removed at least one element. So the size of S prime is at most the size of S, which is M, so it's good. And now we just need to check so the value is better, and we need to check this main technical condition here. So so what are we going to do? So dimension of I prime is what? Yes, so I prime, by the way, is the corresponding set for S prime, right? And then we go by contradiction, so we assume this inequality. So we have that it's greater than dimension of I over 3C. Yes? And then what do we have? Well, this is greater than this D over 3C, which is equal 3C to the power of FHT minus the value of S. Yeah, that's for the D. and now we divide over 3c, so this is -1, which is actually equal, right? Or greater equal, yeah, because we know that the value of s prime is strictly greater than the value of s, so we can write it here, value of s prime. So this shows that s prime was the better choice, for s, and that's a contradiction. So this contradiction proves that that indeed our choice of s satisfies the inequality in the claim, this one, because we assume the opposite. Yes? So are we done with the claim? Not yet. Not yet. What remains to be proven is that our antichain is of size n. That we don't know. Yeah? We just know that we were taking an antichain of size at most m. Perhaps it could be that this extreme choice is somewhere earlier, and we want to show that this can't be. Okay, so move on. So now we assume the contrary, that that the size of S is strictly less than M. And we are going to work around it. So first of all, we need some easy conditional technical work. So we want to look at the poset Q, which is not the entire P, but we want to remove the downsets of S. So yet we need a figure, right? So here is our S, yeah, and we used to look at the upset, and now we want to kill the downsets, yeah. We don't want anything from the down to see anything from the down, including S itself. Including S itself, right? The closed downset. And now we would like to look at our incomparable pairs I, but only those that survived in Q. Yeah? So we do have incomparable pairs in I, and those are incomparable pairs with the second element above everything. Yeah? But the first element could actually could it go below? Not really, right? Because if an element goes below, then it's below all the y's. If it gets below any of the blue, then it's below all the y's, so it's not really incomparable. But there is a corner, there must be a corner case here. I guess the corner case is that y itself, if S would be an antichain of size 1, yeah, which can be, then when you kill the downset, you could, Y is a legal second element here. Yes, and then you could consider so X is somewhere on the side, and you consider an incomparable XY. And this is counted in I, but it's not counted in IQ. Yeah, so this kind of stuff. What I just want to say is that if you look at I minus IQ, then possibly you can have some incomparable pairs there. It's a corner case, but it's possible. But this set is reversible. And then then we simply are building on that the dimension of the rest IQ is really large. It's at least the dimension of the initial thing minus 1. Okay, and now on this poset that we want to look at, on Q, yeah? So let me remove this stuff from the picture, yeah? So without these blue elements as well, yeah? That's Q. But you might still have elements on the side actually, right? This is fine, yeah? There could be huge poset on the side, yeah? So this is Q. And now on Q, we want to apply the lemma. So by the lemma, what do we have? We know that there exists an element, yeah, such that when we look at the dimension, so this dimension is in poset Q. Let me remind it here. When you look at the incomparable pairs that are in our set that we look at, so IQ. So again, y's in those cones, yeah, x anywhere. And now you restrict it to this Q. So Q should be also below y in poset Q. Then there exists such a Q such that the dimension is lower bounded by the dimension of the full thing, yeah, over C minus 2. Yeah? That was our statement, yes? Given that we have a set of incomparable pairs, presumably of large dimension, we can localize that. We can find an element which carries the complexity. So this is our red element. And it is somewhere, right? It could be like here, say, but perhaps it's somewhere here, right? Let's take it here, because it's more fun. And now we do the same trick, right? We want to say that, okay, so first of all, we need to clarify the stuff. So I wrote here dimension of Q under poset Q, but this is actually the same as we would look at the dimension of this set of incomparable pairs in P. This simply comes from the fact that an alternating cycle in Q, that Q is an induced subposet of P. So an alternating cycle in Q, a set of pairs is form an alternating cycle in Q if and only if it forms an alternating cycle in P. Yeah, given that the set of incomparable pairs is in Q already. Yeah, so that's why it doesn't matter. Yeah, and we can look at the dimension in our original poset. Yes. The second thing, maybe perhaps to notice, is that we applied the lemma and we put here C. C was also defined in terms of P in the cover graph of P, but the cover graph of Q is just a subgraph, actually an induced subgraph even, but it doesn't matter now, of P, right? So, and going into the subgraph, the weak coloring number cannot increase. So the inequality is good here. And we can indeed put here C for the weak coloring number of the original cover graph. Okay? So that's the minor comments around this statement. It's all good? By now? Yeah, if there will be a question, we can handle it later on. So, what are we going to do with this cube? Well, it must be the same. So S prime will be equal S minus the downset of q plus q. Yeah? And I prime is the corresponding stuff, yeah? So I prime will be this, yeah? And now we just need to look if everything clicks. So so let's have a look. So what remains to be proven is that that the S prime was a better choice for S. That's where we're heading. So so let's have a look. The dimension of this set of incomparable pairs x, y, I, q, such that q is less or equal I in P. So this is from what we seen there is greater or equal than dimension of IQ over C minus 2, yeah? Which is greater or equal than dimension of the original I. So now I'm shifting from IQ to I, so I'm going over this little difference. And so there is an extra -1 here over C, so I lower bound it by putting -1 outside the fraction. Yeah. Now this is greater than free C coming from this, yes? So free C FHT minus value of S. Yeah, now we still need to divide it by C. Yes. Minus 3, and then and now the final thing. I didn't comment on that. So value of S prime again is strictly, well, not this direction, strictly greater than the value of S. Why is it so? Well, the same story, right? It's not given that Q. It's not given that Q is above something. If it is above something, we remove that something, we put Q, but Q has a strictly larger height. That's good. The legs of it is larger. But now Q could be on the side, and then this is empty. But then we just increase the set, yeah, extend the set S. We have a new element, and clearly the superset has a higher lex order. And here it's critical. Here it's critical that we have assumed to contrary that S is strictly less than M. So we have space. Okay, very good. But then this is so first of all, the value indeed is greater, but we are still in the scope. Yeah. So for example, it is at most FHT -1, which is the largest possible index. Yes, so all this should quickly give you that here you can write free C. So you're missing some free this should give you that this is value of S prime. And this says that S prime was the better choice. For S. And that's a contradiction. That's a contradiction of our assumption here. So indeed we have that the S that we have chosen not only fulfills the inequalities, this one, the tricky one, but also is of the right size, is of the maximum size. And that completes the proof of the claim. Okay. So this way we completed the first step on our way to get the shallow subdivision of KT in our cover graph. Just starting from the fact that the poset has huge dimension. Huge in terms of the height, also in terms of the size of the click that we are heading for. Also huge in terms of the wcols number actually, which in our setup actually is might be growing with the order of the poset, right? As we remember. Okay, so since we are done with the claim, we're going to fix S, antichain S, and this set of incomparable pairs I. Given by the claim. And we are going for another claim. This claim will have a statement that is already interpretable in terms of the target subdivision. So there exist disjoint sets V, subsets of element of P, and R, subset of our antichain, such that, point 1, the size of P is T, and the size of R is at least M to the H, which is to the minus T, which when you read the definition of M, it is T choose 2 to the H to the T to the H to the minus T now, which is actually T choose 2. So R is of size at least T choose 2. And second thing is that for all pairs VR that belong to the V cross R, there is an element P in the poset such that V covers P in the poset, and the downset of P intersected with our set R is just R itself. Okay, now it's again time to draw what's going on here. So please recall that we have the as antichain S. Yes. This antichain this is an antichain, and the size of this antichain is n. So now the claim is that we can find R, which is a subset of S. Yeah? And this R will be still large, but we have a vast thing to choose from. So that's the R. And now we will have some elements D, elements of the poset. So I will draw them here above for a good reason. So that's V. And these elements will be our branch vertices of our model of KT. So that's why it's t of them, yes? The size of v is t. And we have a very special property, yes? So whenever you look, now I'm reading out the item 2. Whenever we look at the element v in V and element r in R, yeah? Then there is an element here that is covered by v in the poset. Specific element, say this one. Its name is p. Such that when you look at the downset of p, you just hit R. Among all the blue points in R, you just hit R. And this is true for every choice of R, yeah? So every guy has a private guy, yeah? You just branch off down in the poset from V, and you find a private downset to go to one of your distinguished elements in the antichain, okay? And this is true for this guy V, but this is also true for this guy V, yes? And so on, okay? This is our statement, okay?
But they are distinct, like for
The red elements?
choice of P, we have another guy R or not? Like this was because you called it a private guy.
That's actually a good point.
As stated for a fixed v and r, the p must be distinct. But for a given r, as I vary v, the p might be the same.
So you say this guy and this guy could coincide in going to some guy here. This is not going to be a problem,
Yes.
but please keep it in mind to, I for example, I wasn't aware of it now, like drawing it and having it in mind. That's a good point. But it seems that the statement allows it, and let's try to live with it. Thank you. Okay, so we have a good picture of the statement. Let's try to prove it. So proof of the claim. So again, we are going to through some extremal choice of our two subsets V and R, and we will show that this extreme one is fulfilling all the conditions. So choose V subset P and R subset S in such a way satisfying item 2, yes, so there's this, they satisfy that one, and the size of B is equal J, and the size of R is at least m to the h to the minus j, which translates into t choose 2 to the power of h to the t minus j. That's from the definition of m at the beginning of the proof. So we want to choose this one, and now what is our preference? Well, the preference is that we want to have j, which is at most t. We're heading for t branch vertices, and we wanted to have it as large as possible. And the thing is that we choose it, we choose V, we choose R, and we are actually let's point out first that this is well defined. Do we see it, that it's well defined? Well, we can always choose, I hope, V that is an empty set. And then as in R, we could choose everything in S. And then please note that, so J is equal 0, R should be greater than M to the H to the 0. H to the 0 is 1, so R should be at least M, and S is M, so this is good. And we should satisfy 2, but the 2 is vacuous because V is empty. Okay, so it's well defined. It's well defined, and now what is wanted again is that actually that J is equal T. Yeah? We want to say, okay, if we chose it this way, our V actually consists of T vertices. And this will complete the proof of the claim. Okay, so assume to the contrary. That J is less than T. And effectively, we're going to give a recipe where to find a new vertex V for V, okay? New element for V. So yeah. So first of all, let me look ahead a bit. Yes. So first of all, what are we going to do now is, can I put it in? Not really. I might have a board here. Okay. So first of all, please note that for every vertex V in V that you have, possibly it's an empty set, right? But for everyone there, and for every one R in R, which is obviously in S, we have that R is less than V in P. Yeah, this is simply a consequence of the second item, right? Yeah, the second item is even more involved, but specifically it means that the red guy is above the blue guy. Every red guy is above every blue guy. Yeah, that's implicit here, right? So that's what I'm writing here, and then by the first claim, by this one here, okay? We are going to have fun. So I would like to look at the dimension of the set of incomparable pairs in I, such that Y is not in the upset of V. Yeah. So let me remind you, what are we doing here? We have a setup with V and R, and I am just trying to find a new red point. I'm just trying to find a new red point. How do we start the business? Well, we just exclude the upsets because we intuitively feel that this is not the place we should take a new red point. So let's look at our complex stuff, complexity, yeah, that should drive the existence of this minor. And let's look only at those pairs that the second element is not in the upset, okay? And here, well, first let's quickly see that this is the dimension of everything minus what? Now I can go over each red element, yeah, and I could just have the dimension of the corresponding set with second elements above the red element, yeah? Yeah, so V here is this red element and V is this one. So what I'm saying is I can take everything and I am removing subtracting the complexity of each upset, yeah? And this clearly is this is a lower bound. We, as the sum of this, like upper bounds the complexity of the stuff that I remove. Yeah, because I just take the sum of the complexities, yeah, which is not really always the complexity of the sum. So okay, so that's good. And now I guess now it's the moment for the claim, right? So maybe we should take it here. So now we are writing that this is greater than dimension of I minus the size of V times dimension of I over 3C. Yeah? Well, let me remind you. We are working with a set of incomparable pairs I, such that whenever we pick an element which is greater than at least 1 in our blue set, whenever we take an element, like this one, now it's important that we have that our V and R is disjoint. Yeah? So it's really strictly above, they don't coincide. It's strictly above. Whenever we take such an element and we look just at the set of incomparable pairs over there, then the complexity goes down. Okay, so here, because we have a negative sign, we have a lower bound. Yeah, that's the lower bound for each of the sets. We have V sets. Okay, so now some elementary algebra. Dimension of I, and this is 1 minus, now V is upper bounded by T, yes? So instead of the size of V, I put T here. And now, dimension of I, this is taken out, so this is 1 over 3C, right? So now it's the moment that I want to use that C is greater than T. Yes, so I can replace this T with C. So then I have that, that this is dimension of I times 1 over C over 3C, yes, which is 2/3. The dimension of I is at least 2 by this border thing for the for our claim. So this is at least 2 times 2/3, which is greater than 1. Which means that this set is not empty. Okay. Yes?
An empty set has dimension 0 or 1?
Dimension 1. But here we have a strict inequality.
Yeah, I see.
Yes. That's just by convenience. I mean, this way you really can say that then the dimension of whole pole set coincide. That's really not important. Yeah. And we must kill it, yeah. We could drive it as large as we want in terms of a constant, so if it's 1 or 2, it doesn't matter. Okay, so what we just achieved is that there is a guy which lives out there and avoids all the upsets, yeah? We're going to fix it, we call it Y. Okay? But let me make some space now. I think we made a good use of this claim, the first claim, and it can leave the board with glory now. In glory. Yes?
Why is the best name? Because it appears quite
true. That's true. Perhaps we take another name. It's just it's true that y was usually our iterator. Let's call it y star, yeah? You're right. So, yes. So choose y star here, yeah? That's the last thing we did. Now, but you know, it is not yet, our y star is not yet a good guy. It's not yet a good candidate for red. Why is it so? Well, try to reason out intuitively. The red guys should have this property that we should be able to branch into the direction of any blue guy. Yeah? And we have a freedom to take a subset of the blue guys, that's true. But still, it can happen that actually it's covered just by one element here, right? And all the stuff is below actually this element, and then this y star will have no branching, and you are not able to fulfill the second item. So this is not going to be our new element of V, but it is a good starting place. And now we set up an algorithm that goes down in the poset from y star and finds a good element. So let it be. So set V to start with y star, and then as long as there exists an element x in P such that x is covered by V in P. And what is important, the downset of x intersected with R is great, the size of it is greater than the downset of V intersected with R. And now, and now we take some multiplicative factor, which is n to the power of h minus j plus 1. We update v to be equal x. Yeah, and we iterate. Okay, so let me try to again illustrate what is going on here. So V is starting from y star, yes? And now, perhaps there is x. What is x? Well, first of all, x is covered by V, yes? So it's one of these elements that are just below. And then, but it's a special one. So you look at look at this guy, for example. Perhaps this is x, yes? So what do you see? You look at what are these elements in R. So what is the number of these blue things that you are still above? Please recall that starting from here, you're above everything. Why? Well, because this y star was taken from the set I of incomparable pairs, and these set I, that was the second element of the pair, and these elements are above everything in S, above all the blue stuff that we ever had. So in particular, above our distinguished blue stuff that we have in here. R is a subset of S. Yes? But now perhaps that we are going down, and maybe we lost track, yeah? Maybe when we look at the downset now, we don't have everything. Yeah? So we have a number. But as long as this number is large, so as long as this number is at least this number that we had just a moment ago, this always dominates this. And as long as it's a fraction of it, and that's the size of the fraction that we insist on, we are going there. So we are walking here and we are going down as long as in this one step that we are making at the time, we are keeping some fraction of the total things, blue things that we are above. As long as we keep this fraction, we go down. And so when are we stuck? Actually, we are stuck at the moment when we are above some stuff. So this will be our V, right? Our resulting V, hopefully. And we stop there if whatever step we take, yeah, when we make this step, we suddenly lose a lot. Yeah, we are covering a number of blue things. We just make any direction we take, we lose a lot. Intuitively, at this moment, we will have large branching, and we will build on that. But in order to set it up, we need to argue actually that, for example, it terminates. Well, it does terminate because the heights of V go down, are decreasing. Yeah. So the process terminates, yeah? That's good, right? That it terminates. Now, the second thing I want to share with you is that this guy never gets down to a minimal element of a poset, nor to some blue element. We never get down to those. We start from being above a number of them, and we never get down to get to the blue, or another corner case to a minimal element of the poset. Yeah. Why is it so? Well, in order to see it, see that after h minus 2 steps, 2 or less steps, what do we see? So our current V, after this number of steps, yeah, well, clearly the number of steps is at most h minus 1, because that's the number of times we can go down before we hit the minimal element. But now I take h minus 2. And so when I look, what is the number of blue things that I still have? And now my intention in this line is to tell you that I'm still above a lot. Because I was above a huge number, and I was giving up just a fraction. So I'm still above a lot. That's my intention here. So now let me convince you. So this will be greater than the downset of y. And so this is y star now, right? The downset of y star intersected with r, the size. And now in each step, I was going down by m to the h to the minus j plus 1. And I'm doing it h minus 2 times at most. So this is the thing. And now, so this thing, so this set actually is equal r. Yeah, because we are starting, I mentioned that. I'm starting from an element which is above all the blue. So this is just all the blue. So this is r over, again, this number in the denominator. And now when you do the math here, you can so okay. So first of all, you have a lower bound on r. Yeah, you see, we have a lower bound on r. So we plug it here, and we combine it with this thing here, and then you will see that this is at least h to the minus j plus 1. That's the intention. That's the intention of the choice of the fraction. So now I'm here, which looks basically like this, but instead of j, it's j plus 1, yeah? So okay. Given this, now, so that was my intention. To have v after a number of steps, and you're still above a lot, okay? And now, please note that if now, so that's our v, yes? And then, could you get from v to x, which is a minimal element? Well, if you are a minimal element, above how many blue things you are? Well, at most 1, yes, because you're at most, you are just above yourself and above nothing else. So if this is blue, that's 1. That's 1, yes? But now what is so the size of this downset is at most 1, yeah? But this guy here is this, and now I divide it by the same. So I have 1 here, and I need to have a strict inequality. I can't get it. So I will never make this step. I will never make this step towards the minimal element. So that's one thing. And the same thing applies if I want to make a step just on the blue element. Yeah, and here I'm using the fact that the blue elements form an antichain. So if I hit the blue, I am just above this blue and above nothing else. But my D here is still of this size, yeah? So divided by this, it's 1. It's at least 1 on this side. And on this side, it is 1. So I will never make this step. Okay, so this proves, so we did prove that the process terminates, and moreover, we end up with an element, yes? We end up with an element which is not the minimal, which is not the blue one. Okay, so that V that we got into is our new element in the V. Okay, this is what we do. So we are heading to say now that V prime is equal V union the V. Okay, the output V of the process. Yes. So now we need to define we need to define R prime, which will be the subset of R. We're not going to take all of them. We can't take all of them. This should be immediate for you, yes? Because we went down, and on our way down, we gave up some blues. So it's very likely that we are actually not above all the blues here. But we are above a lot, and this will be enough. And the branching will come from the fact that everything that we cover is not above a lot. Okay, so yes, we move on. Maybe I will leave the setup of the proof of the claim. Might be still useful for conclusion. So, what are we going to do now? So first of all, let's Z be the set of all elements. Elements covered by V and P. Okay, so these elements here, right? Yeah, this is our Z. Okay. Now, please note that we already know it's not blue, so V is not an R, and from that I simply know that when I look at the downset of V intersected with blue, then this is just the union of the things that are the downset of the green elements. So I can just write that this is embedded in the downset of all the green. Yeah. The only thing that it wouldn't be satisfied is that when this one would be blue, but it's not blue. Yes, we did argue that it's not blue because we argued that the process doesn't stop at blue, and V is the vertex that we take, that the process has stopped. We argued that it's not a minimal element, and we argue that this is not blue. Okay? So, yeah. So now we take a Z prime, which is inclusion-wise minimal subset of Z. Such that D of D intersected R is a subset of D Z prime. Okay, so what is the intuition behind Z prime? So Z prime is the subset of blue elements, of green elements, let it still be green. So now, you know, from V going down, I hit some blue. And then, so I want to take some green elements here, such that when I look at their downsets, I cover all the blue that is hit from this downset. So definitely if I take them all, I'm good. But maybe I don't need to take them all, because maybe some of them are covered by more than one green, and then I don't need to take all the greens. So I just take enough greens, yeah, so everything in blue is covered in the downset. That's Z prime, okay? Any inclusion-wise minimal set will do. That's Z prime. So now these greens that I really care on is Z prime, and that is a subset of Z, okay? Yes, so now from the minimality, yeah, we can have some witnessing elements. So this allows us to fix for every Z in Z prime, an element RZ, so this will be blue element in the downset of V intersected with R, such that what? Such that first of all RZ is in the downset of Z, and second, RZ is not in the downset of Z prime for every Z prime in Z prime minus Z. So, you know, just from the minimality, if I have taken this guy, what does it mean? It means that if I don't take it, then I don't cover all the blues. Yes? So what does it mean? That means that there is a blue here. There is a blue here in this downset. Yeah? That is not in the downset of any other things that I distinguished. Yeah? For each guy that I have distinguished, yeah, I have a blue, which is private in its downset. Yeah? For each guy that I distinguished, I have a blue that is private. Okay? That's straight from the minimality, right? Okay, so now now what I want to say. I want to say that since the process stopped here, so intuitively we have a large branching, I must have that the number of distinguished guys is large. Okay, so that's first thing to do. Okay, so yeah, now perhaps I erase this. So I just told you that before, I tell it again, that B prime will be D union D. And now I'm just about to define new R prime now, that I announced before. So R prime will be just those representatives. So I'll just take RZ for each Z in Z prime. Okay? So that's the B prime and that's the R prime. And now I can write wanted again. So wanted now is that B prime, R prime was a good candidate, was the better candidate. For VR. Okay? So now, miraculously, we do have the definition of V and R. So please have a look. So first of all, note that V prime is indeed larger. Yeah, this is because we started from an element which was not in the upset of the red, and we were going down, and we found our favorite element. So this element cannot coincide with the reds. So this means that V prime is indeed larger than V. V was of size j, V prime is of size j plus 1. That's good. So this will mean that indeed it will be better if the conditions are satisfied. So what about the conditions? So in the condition part we insist so that 2 is satisfied. So 2 is this important thing. Let's leave it for the end. We also insist that the sets are disjoint. Yeah, so that V prime and R prime is disjoint. This is true because this simply comes from the fact that this guy is not blue. That's just an immediate fact from that. Next thing is, well, the next thing we want to show that, so we have that V is of size j plus 1. We need to show that R is of decent size. Yeah, so R prime walks with the size of V prime. V prime is of size j plus 1. I need R to be of size at least n to the h to the, and here should be j plus 1. We need that. We need that R prime is large, and we didn't say a word about it. So let's do it. So first of all, note that a representative is distinct from another representative, given that Z and Z prime are in Z prime, and they are distinct. This comes, this comes from the fact the definition of representatives, yes? So, what are we talking about? Z and Z prime, 2 green elements. Yeah, this representative is only in this downset and in no other downsets. So indeed, this blue is distinct from this blue, given that this green is distinct from this green, right? So this gives us the property that the size of R prime is actually equal to the size of the Z prime, yeah? Intuitively, I had it on this picture. The number of greens is exactly the number of blues. So I need a good lower bound on the blues, on these blues. So I will get it from the lower bound on the greens, and the lower bound on the greens goes here. So the downset of V intersected with R is exactly the downset of Z prime intersected with R. These sets are even equal, right? Because we took Z prime in such a way that it covers all the blues that are hit by V. So this is good. And then we upper bound the size of the set by the union of the sizes of its subsets contributing to it. So this will be intersected with R, and now we go over all elements of Z prime, yes? And then this should be bounded by the size of Z prime, and now each of these sets is bounded by the fact that the process has stopped. Here I use it, yeah, because you see I'm upper bounding stuff, I'm here, I need an upper bound on the size of the number of blues hit by something that I cover, but we stopped here, so anywhere I go I don't cover a lot, so this is where I plug it in, and when I plug it in it's the size of the older blues, yeah, of the older blues that I see below V, yeah, divided by this factor that I allow, which is J plus 1, yes? Okay, so we have this thing, and here we have dV intersected with R, dV intersected with R. So when we cancel it out, we get that we get the lower bound on Z prime. So we get that Z prime is at least M to the H to the minus J plus 1. Yeah, and this is as discussed here, this is exactly R prime. So we do know that our R prime that we take is large. There is only one last thing to discuss, which was implicitly covered. So we need to say that the item 2 holds, right? So what does it mean? Whenever we take a V from here and R from here, there is a private way to go that we see under this R. So it was true for the old V's here, and even for the larger set of blues. So it is true when we take just a subset of blues with respect to those. So all we need to discuss is the new red. But for this new red, we just devised it such a way. Yeah, we just left those blues that are really like that. That each blue that we have, there is exactly one direction from V that we go down, and we just see that blue. So this means that item 2 is satisfied. And this really means that that V prime R prime was the better candidate. So it's a contradiction, and this contradiction is with the fact here that we assumed that our set V is not saturated. Yeah. So really, our set V is of size T. And we have our T branch vertices. Okay, so claim has been proven. Okay, so we are really done, although we can't really say it loud, but we are done. So after that claim, we can fix V and R. Yeah. So V's are here, right? The size of V is T. And we also have R. Yeah. And the size of R is at least T choose 2. Let's take it to be T choose 2. Let's just take a subset, yes? So it's T choose 2. So now we're going to use those vertices, our branch vertices, and the blue vertices will serve us as a transmitter for the edges. So now for any two elements of V, V1, V2, yeah, we fix an element R for this two subset, yeah? So each two subset here has its private blue element. We fix it arbitrarily, yeah? And now look at this, yeah? So from this here, there is a guy that we take the direction of so that its downset just sees this blue and nothing else, yeah? And then from this guy, there is a direction that this guy just sees this blue and nothing else. And now we just take any chain. So there is a chain down here, there is a chain down here, yeah? The union of these two chains clearly consists a path in the cover graph connecting V1 to V2. Okay, so we do it for each two subset of V, we do that, and we claim that these paths don't intersect. Well, what we really claim is that if you have V1 and V2, and it's distinct from the subset V1 prime, V2 prime, then and if this path is Q V1, V2, yes, then the only way that the two paths, let's make this path yellow, yeah, why not? The only way that the two paths can intersect is on their endpoints. Yeah. So let's assume the opposite. Let's assume that we have an internal vertex Z such that belongs to one path and also belongs to the other. Yeah. So okay. So we need some. So first of all, note that if Z is here, so all the yellow stuff is above this blue, yes? Yeah, all the yellow stuff is above this blue. So we do know that Z is above R, V1, V2, yes? But now, if Z is also, it belongs to this other path, V1 prime, V2 prime, yes? Then this immediately means that Z is also above the other blue element, V1 prime, V2 prime, yes? Because there is this other path here hanging, right? Green one, yeah? I don't know. So then we are above something else, yes? Something else because the pairs are distinct. So the R's are distinct. Oh wait, that's almost a contradiction. It is a contradiction now because Z, Z is either below this guy or below this guy. Yeah, the path is a union of two chains. Yeah, so this is P1 and this is P2, and without loss of generality, let's say that that P1 is above Z in the poset. Yeah, but Z is above both elements. Yes, so P1 is here. P1 is above the Z. Yeah, but this makes this makes this very element above two blues. And that's a contradiction. That's a contradiction with the fact that the paths intersect on some internal element. So if they intersect, they must share an endpoint, but that's fine with the topological model, right? Okay, so we have a topological model of KT. And what is the size of the paths that we are having here? Do you see why it's 2h now? Well, yeah, I mean the number of edges, it's h minus 1 down and h minus 1 up at most. So the number of edges is 2h minus 2 at most. So in terms of the subdivisions, what we are talking about is the number of vertices inside. So it's at most 2h minus 3 subdivision of KT in the cover graph, in G. So given large dimension, we get a shallow subdivision of KT, which completes the proof of the theorem, and that theorem connects nowhere denseness with with the theory of dimension in partial ordered sets, which is a cool thing. Thank you.